So this is EE610, lecture 6. We have now seen how to implement a common source amplifier. So that we take a transistor to bias this to a given VGS0 using a battery source VDD and two resistors RA and RB. We generate the potential VGS0 equal to VDD into RB by RA plus RB. So this determines a drain current, some ID0 that flows through the transistor. The same current flowing through a resistor RL1 creates a drop across the resistor, and therefore the drain voltage will be given by VDD minus the potential drop across RL1. To connect the incremental voltage source, we have the incremental voltage source. It always comes along with its own resistance Rs, and we connect this through a very large capacitor. And the load is also again connected through a very large capacitor R. Okay. And in the previous class, we saw a numerical problem in which we calculated the operating points, the small signal gain of the circuit, the input signal swing limits, and how to determine what values of C1 and C2 to be used in the circuit. So let's quickly revisit the swing limit discussion we had. When your input signal, when you are dealing with a positive input cycle, what happens to the total VGS? Your input Vs is increasing, which means your total VGS decreases, remains the same, increases, right? Your VGS increases. What happens to your total drain current? Remains the same, increases. Therefore, your total drain to source voltage is decreasing, right? Which means your transistor, we call this as M1, M1 could enter triode region. Now, you can write the exact conditions for it and derive what is the maximum input amplitude that you can apply such that M1 still remains within the saturation region. Now, similarly, during the negative input cycle, your VGS is decreasing, the total drain current is decreasing, therefore the total drain to source voltage is increases, right? So based on this factor alone, the fact that the drain current is decreasing, it tells you that your M1 could enter into cutoff. Right? And in this discussion, we saw that we made an assumption of the system still being very linear when we were doing both these calculations, right? Is that assumption really correct? No, right? Because what was the limit that you calculated for a signal to be called as small signal? Your small signal VGS had to be smaller than 2 times overdrive voltage, right? 2 times whatever was your VGS0, the bias voltage that you have applied, minus VTH. Twice the overdrive voltage. Now, what is the limit that you got when you checked for cutoff region? What is the limit you got for Amax to? VGS0 minus VTH divided by 2, right? So you see that this limit is only 25% of this, right? And we wanted our small signal VGS to be much smaller than twice the overdrive voltage. 25% of a value is not much smaller than that limit. So theoretically, the assumption of small signal is not valid by the time you hit Amax2. So this linear analysis is not a very clean calculation to calculate the limits, right? To calculate the input signal swing limits. But this is a quick and dirty calculation that is quickly giving you a value. And as long as you make sure that your input signal is much smaller than Amax2, then you are fine. Amax2 is like an upper limit. We do not want to operate anywhere close to it. Is that clear? Okay. So the model of the transistor we have been dealing with, especially in saturation region, is ID equal to half mu n COX W by L into VGS minus VTH the whole square. And with this relationship, you had your ID versus VDS plots looking like this. So you had a sort of linear and a parabolic curve till the point VGS plus VTH, and beyond this was a flat constant current. Did I make a mistake here? This has to be VGS minus VTH, right? And if you put a larger VGS, you would see, so if this is your VGS1, this is VGS2, VGS2 is greater than VGS2. This is at VGS1 minus VGS, right? And what did you get for GM value? This was equal to mu n COX W by L into VGS minus VTH. What was your GDS? This was given by dou ID by dou VDS. This was equal to 0. And with all of this, when you calculated your gain, what did you get your gain to be? Minus GM times RL1 parallel R. Okay, good. So when I initially gave you the current equation for saturation region, I told you that there is one more factor here given by 1 plus lambda VDS, right? Where lambda is the channel length modulation parameter and lambda is inversely proportional to the length of the transistor. Right? So you will learn more about this channel length modulation and this lambda parameter in your device physics course. For the purpose of this course, just understanding this behavior is sufficient. Okay. Now, if you have ID equal to half mu n COX W by L VGS minus VTH the whole square into 1 plus lambda VDS, what change do you expect to see in the ID versus VDS curve? So during the saturation region, instead of it being a flat curve, you'll see that this will increase slightly. Right? Do you think there will be a discontinuity at this point? Based on the equations that you have now, there will be a discontinuity, right? At this point, the value will start slightly higher. And then you will see a slope like this. Okay? So for the next curve, again, at the point where it is switching between linear region to saturation region, the value is going to start slightly higher than this, and then it will again increase. Do you think actual devices will have such discontinuity in the IV characteristics? So the actual device cannot be represented using a very simplistic ID versus VGS, VDS function as I have shown. To represent the behavior of this transistor, a lot of parameters are required, and so this is basically a 54 level model. instead of 4 or 5 parameters that we are dealing with, such as mu and COX, VTH, lambda, etc., they have lot more parameters to represent the properties of this transistor. But such a complicated model can be used only for simulations. You cannot use it for hand calculation and expect to finish a design within a reasonable time. So to get very, very accurate results, you will have to use the proper device model file, run a simulation. The purpose of all these equations is to give you quick results, sort of like quick and dirty calculations, that is giving you immediate results, which is reasonable and accurate enough for you to proceed with the design. Okay. So in practice, this discontinuity will not be there. So we will have to work with the equation with a small discontinuity, but as you will see, it will not affect our calculations very much. Okay. So equation of ID is now given by the expression I have shown here. What happens to the equation of GM? So what is GM? What is the fundamental definition? GM is your Y21. And what is the fundamental definition? Dou ID by dou VGS. So now can you give me the expression? Into 1 plus lambda VGS. Okay. What about your GDS? So the entire factor of half mu and COX, W by L, VGS minus VTH square, all of these are constants as far as VDS is concerned. This into lambda. Okay. So you can see that our expressions for ID and GM has changed. They have changed. And the GDS, which was earlier 0, is now some finite value. Okay. And you can also immediately see that calculation of the operating point is going to be a little bit more complicated, because ID is now both a function of VGS as well as VDS. Okay. So now to get around this problem, what we say is this. We recognize that the value of lambda is going to be very, very small. Right? This is an information that we have because of our friends in device physics. They have figured out that the value of lambda is very small. They have shown it mathematically, and they have also experimental proof for this. So given that the value of lambda is very, very small, what approximation can we make? So in calculating the operating point, so when we are calculating the ID, we say that because value of lambda is very, very small, we expect this factor to be much, much smaller than 1. Right? That is, the effect on ID is going to be very small. So for operating point calculations, we will not consider lambda. Right? Similarly, for calculation of the GM, again, lambda VDS is expected to be very small. Therefore, the error we make in ignoring the lambda is not going to be much. So, we will ignore lambda for operating point calculations. And for calculating GM. Right? Now, if you want to be very accurate, then feel free to use VDS in both of these equations and go ahead. You will not lose out any marks if you do that. Right? Maybe there are cases where you want that sort of accuracy and you might prefer to have VDS in the expressions. But for most cases, it's a very reasonable approximation to make. Okay. Now in GDS, if you put lambda equal to 0, right, then the whole equation goes back to 0. But as you can see, the main effect that we see here is that GDS, instead of being 0, is now a very finite value. So we calculate GDS using this equation. Right? And this equation can be simplified into, what does this remind you of? ID. Right? So we simply say this is equal to lambda times ID. So now let us look at what happens to the small signal model of the transistor. So the original model that we worked with, this was your gate. You had a small signal voltage VGS between the gate and the source. Let me show the full potentials here. Let's say this is at some VGS0 plus a small signal VGS. Between the drain and the source, you have some VDS0 plus a small signal VDS. And the current flowing through the drain is some ID0 plus a small signal ID. So now in the incremental model, you have the gate here. You'll see the voltage small signal VGS between the gate and the source, right? And earlier you simply had a voltage controlled current source of value GM into VGS. And this was your small signal drain current. And this was your small signal drain voltage. So now, because of the presence of GDS, you will have an impedance connected here. Okay. So in the presence of GDS, let's see how our gain is now going to change. Help me sketch the small signal circuit for this. So we'll start with Vs. What happens to C1? It's shorted. What is the other resistor? This is RA parallel RB. Across the voltage controlled current source, I now have a GDS. And then what is the other resistor? This is RL parallel RL. Okay, so because I have represented everything else in terms of resistance, instead of GDS, I'll write it as RDS given by 1 by GDS. And what is the current flowing through this? GM times VGS. Now, as usual, we will simply assume that RA parallel RB was much greater than RS. Then can you give me the expression for gain? This is V out. This is Vs. What is V out by Vs? This is minus GM times RDS parallel RL parallel RL. Is okay for everyone? So has your gain now increased or decreased? Decreased, right? Now what is the ideal scenario in terms of the load resistor if I wanted to maximize the gain? I want to maximize the gain. Do I make the load resistor high or low? I have to make it high, right? Let's assume that I make the RL resistor. So let's say I make RL parallel RL1 to infinity. Okay. Assume that we figured out some method to make sure the transistor still remains in saturation, and we made RL parallel RL1 to infinity. This is the best possible scenario I can have, right? In this case, what is the gain of the transistor? This is equal to minus GM RDS, right? And what comments can you make about this gain? This is totally a function of the transistor properties and the bias, right? Is that clear? Once I pick a transistor, certain properties such as mu and COX, VTH, etc. will come along with it. And once I fix the bias, both the GM as well as the RDS are fixed, right? And the maximum gain that you can get out of that transistor is now limited to GM RDS. Now, if you don't choose, depending on how you choose your load resistor and how you choose RA parallel, RB, etc., you can get a lower gain, but you cannot go higher than this, right? Therefore, this property, GM times RDS, is also called as the inherent gain of the transistor. Which is why sometimes when you want a very, very large gain, a single stage amplifier will not be sufficient. You'll have to cascade multiple stages because a single stage can at max give you GM times RDS. Okay. So looks like we started out with a common source amplifier with this sort of configuration, right? And already we have hit a small bottleneck that the moment we take into consideration some of the transistor non-idealities such as the channel length modulation, the gain is now decreasing. So quickly I'll give you a value for lambda. Based on the numerical problem that we solved yesterday, could you tell me what is the new value for gain? Let's say your lambda value is given as 0.05. What should be the unit? It is volt inverse, right? So your ID expression is given by this factor, which was the ID that you knew earlier, into 1 plus lambda VDS. So both sides should have the same unit as ampere. This portion is already in amperes, which means this should be dimensionless. One is dimensionless, lambda VDS has to be dimensionless. So lambda should have the unit volt inverse. Okay. So lambda equal to 0.05 volt inverse. Please tell me the new gain that you get. What is the value of RDS? So RDS is 1 by lambda ID. What was the ID naught that you calculated yesterday? Please look at your notes. 0.5 milliamperes. Right? So this is 0.05 into 0.5 milliamperes. How much is this? This is 40 kilo ohms. Right? So the gain was minus GM times RDS parallel RL1 parallel RL. What was GM? GM was 1 millisiemens. What was RL1 parallel RL? 5K. Now RDS is 40K. Can I ignore 40K with respect to 5K? No, right? It is not very, very small. And now it depends on how much error you can afford to make. Let's say we don't want to make an error here. Can you calculate and tell me what is the effective resistance? This is at 4.44 kilo ohms. So what is the new gain? VDS was set. So we are making an error. How much is this? 4.4. What is the unit? Right, it's minus. So earlier you had minus 5 as your gain, now your gain has reduced. Okay. So now let me talk to you about some of the other non-idealities that you can expect from a transistor, mainly the variation of transistor properties. So the transistor properties that you are familiar with so far are mu and COX, right? There is threshold voltage VTH, then there is W by L, and now you are also familiar with lambda, right? So I'm going to focus the attention on two parameters that see the most variations, mainly mu and COX and VTH, right? So typically, when you are making an IC, so let's take the example of the common source amplifier. Let's say you wanted 100 ICs or maybe 500 ICs. So you will send your design to a foundry, right? The foundry will have wafers which are circular in shape. A typical standard size is around 300 millimeter. So the diameter is at 300 millimeter. And this wafer is then divided into smaller squares where each square is now one IC. So now your design with the common source amplifier will get replicated 100 times, right? And then once it is completely fabricated, they dice along these lines and then give you individual squares. Okay? So this is how you get a single die with a common source amplifier in it, and then you will get it, you will package it and then sell it to customers. So if you design 100 common source amplifiers, ideally you would expect to see the same gain in all 100 ICs. Right? But it turns out these transistor properties will vary during the manufacturing process. So if you take two dies and then compare the VTH of the transistors in the two dies, they are not going to be same. For example, if you nominally expect 1 volt to be your VTH, it can easily vary, let's say between 0.8 volt to 1.2 volt. Right? It could be any value between a range. Now, how wide or how narrow this range depends on how good the foundry is in the whole manufacturing process. They typically try to keep it tightly controlled, but even then you cannot expect this constant 1 volt for all the dies. So this is part of the problem. Right? Now let's imagine that the VTH of your transistor changed. What happens in your circuit? So you connected a biasing circuit like this, right? You gave some VGS0 here and you expected to see a current which was proportional to VGS0 minus VTH the whole square. You knew what that current was. You calculated your GM, you calculated all the other properties of this amplifier based on it. Now, if the new VTH of the transistor has a small variation from the expected VTH, let's say it is the original VTH that you thought it had plus some delta VTH, what happens to the current? The current changes, right? The current changes, which would mean your operating point has changed, your GM has changed, swing limit calculation has changed, everything has changed. How do we proceed now? We made 100 amplifiers, now all 100 of them have different operating points, right? How can we even sell it to a customer? Any suggestions? Okay, so we'll come to the solution in a minute, right? So this is a big problem, right? Now, so the same problem also happens with the resistors. For example, you wanted RB to be equal to 2 mega ohms, right? Now it turns out once you fabricate, you don't have an exact control over this RB being equal to 2 mega ohms. It can vary by up to 20% in most of the processes, right? But the only saving grace is that if you have two resistors, you cannot rely on the exact value of the resistance. but you can guarantee that the ratios are going to be similar. For example, if RB was 2 mega ohm and RA was 10 mega ohm, let's say in your chip, when you got it in your hand, this became 2.5 mega ohms, right? Then it is guaranteed that your RA is also going to change to 12.5 mega ohms. Right? So it is the ratio of RA by RB is going to remain the same. Right? Similarly, if you have two transistors in the same chip, right, and these two transistors are close together, and you take certain precautions during the design, you can guarantee that those two transistors will have similar properties. Right? They might have different VT than what you designed for. Right? You might have designed for a VT of 1 volt, but if one transistor has a VT of 0.8 volt, it is guaranteed that the other transistor will also have the same 0.8 volts. So is it a good thing or a bad thing? So we cannot rely on the absolute values of any of the parameters on chip, but we are sort of guaranteed that they are going to come out similar. Right? If there is one transistor, I can have an identical copy of another transistor and they'll have similar properties. Right? It is a silver lining. Right? This is basically a nice thing because it means if you can figure out a way to correct the operating point of one transistor, you can apply the same correction to the second transistor and they'll work out fine. So anytime you are given a medicine, has that medicine been tested specifically for you? No, right? They have tested it in some clinical trial on an identical copy of you, probably 50 identical copies of you. Basically 50 other human beings. Now because it works on them, we are sort of guaranteed that it will work on us because for the most part, all of us are human beings, right, with similar structure underlying. Right? And any other differences that arise is some random mismatch. So that's the same way how you think about transistors also. So if we can apply a correction mechanism to one transistor, the same correction mechanism can be applied to the other transistors. Good. So now, coming back to the problem, what we have done now is we have tried to bias our transistor with a constant VGS0. Right? Let us quickly look at the difference that causes in GM when mu and COX or VTH is varying. Right? So the expression for GM is mu and COX W by L into VGS minus VTH. Right? Now let's say your VTH, the new VTH, is your old VTH plus some delta VTH. Can you tell me what is your new GM? This is mu and COX W by L into VGS minus VTH minus delta VTH. Right? So if I do GM dash by GM, what do I get? One minus delta VTH divided by VGS minus VTH. Right? I'll add a note here to show that these are the operating points. Okay. So this is when your VTH is changing. What happens if your mu and COX changes? So this is your current factor, Kn is mu and COX. Now if this becomes a new value Kn dash, can you quickly tell me what happens to GM dash by GM? This is simply equal to Kn dash by K. Right? So now if I bias this transistor with a constant VGS0 and if either VTH or mu and COX changes, you expect to see the following changes in your transconductance. So now all of this discussion is beginning from the point that I have biased with a constant VGS0. What other way is there to bias? What else can you think of? I want to determine the operating points. Right? What determines the operating point of a transistor? VGS0 What else? ID and VDS, right? Now among the three parameters, so far we have been trying to keep VGS0 constant. Does it make sense to make VDS0 constant and then look at the biasing? Can VDS0 alone determine the transistor's operating region? No, right? So then the third point is to try and make your ID constant. Okay, so constant VGS biasing is what we have been doing so far. Right? What if instead of making VGS constant, I try to do a constant ID bias? Okay. So when I did a constant VGS bias, I gave some VGS0 between the gate and the source. I of course have to set the drain voltage such that the transistor is in saturation. And now if the transistor properties change, let's say the VT changed, then the current through this is going to change, right? I only maintain the VGS to be constant. So now what we are saying is, instead of trying to make VGS0 constant, I will somehow make the current through this transistor ID constant. Do you think this is possible? Again, I have to set some VDS0 such that it is biased correctly in saturation. Right? So if the VT changes, I still do not want the current ID0 to change. For now, we will not worry about how it is done. Let's assume that we have a very smart battery that is able to detect any changes in the VT and it adjusts itself such that the ID0 remains constant. Okay. Now, given that we have a condition like this, let us figure out how your GM is going to change when VTH is changing and when mu and COX is changing. And then we'll compare both the methods and see if there is a benefit in preferring constant ID bias versus constant VGS bias. Okay. Now, if there is no benefit in doing this constant ID bias, then we don't have to go and figure out how to do the smart battery. We'll figure out some other solution to keep track of the parameter variation. Okay. Now, what expression should I use now for calculation of GM? So, 2ID by VJ0 minus VTH. Everybody agrees? Why this equation? Current is constant. What about VJ0 minus VTH? It will vary, right? To keep the current constant, VJ0 minus VTH will have to vary. So then this equation is not very useful for us right now. What other equation can we use? Right. So we could use 2ID into mu n COX W by L. And we prefer this equation because the term VJ0 is not appearing in this equation at all. Okay. Now let's say your new VTH is the old VTH plus some variation over it. What is your new GM? It remains the same or it varies? So we have done a constant ID bias. We have guaranteed that this ID is not going to change even when the parameters of the transistor are changed. Then it will remain the same, right? So this is going to be equal to GM, which means there is no variation when I compare the transconductance before and after the VT has varied, right? The other method to check is if your current factor varies, right? Your Kn prime is not the same as the original Kn that you started out with. Then what happens? This will be equal to under root of Kn prime by Kn. Okay. So now let me summarize the result we have. We have done two methods. One was constant VGS the other is constant drain current. Okay. In one, if your VTH becomes VTH plus delta VT, what was your GM prime by GM? 1 minus delta VTH divided by VGS minus VTH. Okay. Under constant ID condition, what was the GM prime by GM was equal to 1. Okay. So this is assuming your Kn prime was equal to Kn. Now if your Kn prime changes to, if your Kn prime is not equal to Kn, this is a different value, but we'll assume that the threshold voltage is not changing. Right? Then what did you get for GM prime by GM? This was Kn prime by Kn, and here this will be equal to under root of Kn prime by Kn. Now based on this table, could you tell me which of these two methods would you prefer? Okay. If you bias with constant VGS, which was what we had done for our amplifier, we see that as the transistor properties are going to change, there is going to be a larger variation in the GM. Right? As your VTH changes, as your mu and COX changes, the GM is going to vary by a larger ratio. Whereas if we somehow figure out a method such that the voltage here will track itself to keep this ID0 a constant, then we see that the variation you would see in GM is much smaller. Right? So constant ID biasing is more immune to variation in the transistor parameters. Is that clear? Do you have any questions? Alright, so now we have concluded that we would like to have a constant ID flowing through our transistor instead of having a constant VGS between its gate source terminal. Now we simply have to figure out how to implement it. So what is your suggestion? Compare it with a current source. Okay, is that your suggesting? Add a current source through the drain. Okay, so this is the circuit you have suggested, right? Now, if I do this, what comment can you make about the voltage here? This is same as me turning this fan and expecting that switch to turn on magically, right? VGS is the cause. This is a unilateral device. Just because you plug in a voltage, just because you plug in some current here, it doesn't automatically generate the voltage here. So there was another example that my professor had said in the class. It's a little unappetizing, but I think that will get stuck in your mind more than the fan example. So you eat food, then you go to the bathroom. It doesn't mean that if you go to the bathroom, food is going to come out of your mouth. Right? So this is a unilateral device. You apply a VGS, then the current will flow through it. Right? Doesn't mean if you push in the current, that VGS is going to get applied here automatically. Right? Now, this is not true for a lot of devices. For example, if I take a resistor, right, I can write the equation for the resistor. Let's say this is of value R. I could write V is equal to I into R or I is equal to V into R. Right? Mathematically, both are correct. And even implementation wise, if I connect a voltage V, then the current flowing through this is going to be I. Right? And if I connect a current I, then the voltage developed across this is going to be V. Right? The same thing is not true for a MOSFET. I can of course find out the value of VGS given the current. Right? For example, ID is half mu n COX W by L into VGS minus VTH the whole square. I could rearrange this and say, what is the value of VGS? VTH plus 2ID by mu n COX W by L. Now, I can rearrange the equation and calculate VGS given ID, but that doesn't mean that if I only apply ID, the VGS is going to appear here automatically. So we have to figure out some mechanism. Okay. Now the most logical thing that I can immediately tell you is, I take a transistor, I go buy a battery, I put this battery here, right, and I connect an emitter here. Right. To calculate the current through this, to calculate the relationship of VGS and the current, I just need to know two parameters. I need to know what is mu n COX, what is VTH, right? I make sure that the voltage here is such that the transistor is in saturation. I give some VGS1, I find out what is ID1, then I change the battery, put VGS2, find ID2, then I know what is mu n COX and VTH. Is this enough? This looks okay? Then I'll tell you the problem with this, right? So one, even though we talked about, we write our equation in terms of mu n COX and VTH, like I said, the actual transistor properties are slightly more complicated. If you wanted to exactly map the values, you will need to have lot more parameters, right? And two, all of these, while the property is going to change from chip to chip, it is also going to change from time to time, especially because of the temperature dependence. So even if I find out a particular value for mu n COX and VTH for this transistor, let's say I figure it out with a reasonable accuracy. Now I might have done this measurement at 11 AM in the morning in Kanpur, right? Probably in the month of May. Now if I repeat the measurements in the month of December in midnight in Kanpur, because of the temperature differential, you will get a very different value for mu n COX and VTH. So even if I take a common source amplifier, figure out all of these values and set a particular VGS 0, I sell it to the customer. By the time the customer operates it, the customer is operating it at a different temperature, the gain of the chip would have varied. So this is not a very good solution, and this is what we call as a open loop correction. You correct it once and then you hope that it will work for all the other times. Right? Now, a lot of you are working in the core lab for ESC 201. Others would have done experiments in your previous classes, right? So this is like me telling you, if you are not aware where core lab is, I'm telling you the directions. I'm telling you head north for 45 meters, turn right for 95 meters, and then walk for another 110 meters, turn left, walk 24 meters, and then you'll find the lab on the left side. And this is the actual instruction I printed out from Google. Right? If I give you this instruction and I, take you down to Western Labs and say, just follow this instruction, how many of you think you will get to the core lab? Right? Somewhere along the path, you're likely to, maybe miss one turn by a few meters and you will end up at a very different location. So this is an open loop correction, and if possible, we would like to do a closed loop correction. So now what do I mean by closed loop correction? So I take the same mechanism, right? Let's say I wanted a current IRef to be flowing through this. I connect a battery here. Now I measure what is the current. So I wanted IRef, but when it is measuring, let's say it measured the drain current ID. Right? I see that my ID is greater than IRef. Right? Then what do I need to do to the VGS? So this is the observation, and I need to take some action on it. Right? And what is the action I need to take? I need to reduce VGS. Right? Now I keep reducing Till what point? Till ID becomes equal to IREF. Right? Now, if your ID was lesser than IREF, then what do I need to do? I need to increase the VGs. Right? So, this is a closed loop control. You are continuously looking at the difference that you need to correct, and then you go and tune the battery according to that. This is like me giving you the Google map and then telling you follow this location and then you'll get there. So throughout your walk towards the core lab, you're making sure that the error between your location and the path shown in the Google map is small. Right? Anytime you divert from the path, the error increases and then you try to correct for it. Right? So what is the error parameter here? You are comparing ID and IREF. Right? You're talking about ID being greater than IREF or ID being lesser than IREF. So what is the error that you're trying to correct? ID minus IREF. Right? So you're trying to make sure that the error given by ID minus IREF is tending to 0. So anytime you talk about comparison, you're basically taking a difference. Right? Now, I want to get a subtraction between two currents. How do I do that? So let's say I had I1 coming here, right? And let's say I had I2 also coming to this node. If I wanted to sum these two up, what do I do? What do I do? I should connect them and take out the total current. Right? So this is going to give you I1 plus I2. Now if I2 was flowing in the opposite direction, so this is I1, this is I2. Now if I take a branch out like this, what is the current flowing into the branch? This will be equal to I1 minus I2. See, that's all I need to do. Right? So now, like you suggested, I need to first bring out an ideal source IREF. So much like how you didn't question me whenever I introduced a battery of VDD, I expect that you are not questioning me about how you get a ideal current source IREF. This is something you will learn in advanced courses. There are specific ways in which you can get ideal voltage sources and ideal current sources. For now, let's assume that we have an IREF source with us. And then we connect it to a MOSFET. And we have connected a battery which is tunable. Now, if IREF is flowing through this and some ID is flowing through this, if I take a branch out like this, I would expect IREF minus ID to flow into it. So now I have not connected this to any other node. I just told you that the difference current is flowing here. Where do you think it is going to flow out if I simply connect a wire like this? So if I have to, the KCL has to be, if IREF and ID are two different voltages, right? And if KCL shouldn't be violated, right? It means it is flowing into something. Or the other possibility is IREF is greater than ID and a lot of charge is getting accumulated at this node. Okay? If charge is getting accumulated into a node, what happens to the potential at that node? It has to increase. Right? So a nice way to think about it is, you can think of an infinitesimally small capacitance connected to this node. Anytime you take a circuit with wires, right? Every node is going to have some capacitance, parasitic capacitance associated with it. So this is not a very absurd thing to imagine, but let's imagine a very infinitesimally small capacitance connected to this node, and this difference current is flowing into that capacitance. So now if IREF minus ID is positive, you have a positive current flowing into the capacitor, and the node voltage here, so the node voltage at the drain is increasing. So again, your observation is IREF minus ID is greater than 0 and your drain voltage is increasing. And what is the action you need to take now? What should you do to the gate voltage? You also need to increase your gate voltage. Right? Now, the opposite scenario is if Iref minus ID was lesser than 0, what happens to your drain voltage? This is going to decrease. And what is the action you need to take? You need to decrease this VG. So now you can either ship a tiny human with every common source amplifier to look at this potential and change this VG, or what else can you do? Right? You see that the behavior you want here at VG is anyways happening at VD. Right? So instead of having a separate battery, let's say I short both of them. Now what do you think will happen? If your Iref minus ID is greater than 0, which means your Iref is larger than ID, your VD potential is increasing because you have shorted it to the gate potential is increasing, VGS is increasing, ID begins to increase. Okay. And at what point is it going to settle? When Iref is equal to ID. Right? Now, if your ID was larger than Iref, right, which means your drain potential is now going to reduce, right? And your gate potential is reducing. Therefore, the gate to source voltage is reducing, which means the ID value is now also going to reduce. And it will keep reducing till Iref becomes equal to ID. So now this is a closed loop system and this has a negative feedback. Much like when you were following Google Maps to get to core labs, at every point you were trying to make sure that the error between your position and the recommended position is small, right? And if it deviates, you try and correct it immediately. You're trying to make the error go to 0 based on the feedback. The same thing is happening here. You determine what the error is, how to sense it, determine what action needs to be taken, and then figure out how to do that action based on the sensed error. Now, this is this sort of mechanism, right, where you first figure out what needs to be done in English. If you can verbalize the problem and you can verbalize a solution to the problem, then the rest of it can be done in circuits. That is not the hard part. The hard part is figuring out how to do it in English. So, any questions on this? If ID is equal to I, then VGS will not be? VGS will be 0 is what you're telling me. So, let's assume that VGS is equal to 0 volt. Right? Then what is the value of the current? Current will be 0. Right? If VGS is 0, you always have to calculate the current based on the VGS value. So, if the VGS was 0, then the current is 0, which means IRF is getting pumped into this capacitor, potential is increasing, the gate voltage potential increases. So, as your VGS increases from 0 to a larger value, you will start to get a finite current, and it will keep increasing till this current becomes equal to I. So, take a minute and see if you have any questions on this. Right. So, finally, the voltage VGS0 that is developed is given by this equation. Right. Now, we did all of this assuming that our transistor is remaining in saturation. Is our transistor still in saturation? Is it guaranteed to be in saturation? Right? Why? Because now your VDS is same as VGS, which is guaranteed to be greater than VGS minus. So we did all of this so that we could bias our transistor, our amplifier transistor, right? So let's say this was the transistor that we had earlier. Initially we set its the gate to source voltage using a contraption like this, where the gate to source voltage was maintained as a constant. Okay. Now I want to replace this with a battery, right, that is able to track any variations in VTH. Right. I have also figured out this contraption where if I connect the drain to gate of the transistor, I am guaranteed that the same reference current is going to flow through the transistor. Now, can you recommend some solution wherein I could replace the voltage here such that the same current IRF is flowing through this? Is that clear? What is the voltage here? This is the required VGS0 now, right? And this VGS0 is basically an intelligent battery for us. If your VT is varying, the VGS0 is going to vary with it. Right? So now I want this VGS0 to be applied here. So I simply short both. That's all. Right? So I remove all this RA-RB and I connect the new mechanism. Say this is M1, this is your M2. Now, does this guarantee that IRF is going to flow through this? Everybody is, it guarantees that IRF flows through this provided transistors are matched, right? So like I said, it is possible to match a couple of transistors on a chip. I can make sure that if this has a certain VTH and MUNCOX, this will also have identical properties. So if I have done some feedback method to correct for its VGS, the same thing can be applied to the other transistor. Right? So I'm assuming that both of them have the same W by N. Right? So two identical transistors. So if so, the same IRF is going to flow through M1 provided the channel length modulation is negligible. Because your drain current is a function of both VGS as well as VDS. Right? So if the channel length modulation is negligible, then the effect in the current due to VDS is very small. Right? So for now we will assume that the channel length modulation is negligible. Then the same IRF is going to flow through M1. So I have biased my M1 with a very smart battery. Now I need to connect my small signal source. How do I do that? So at this node, I want to see VGS0 plus small signal VS. Small signal, VGS. How do I couple a small signal source here? Through a capacitor. Then your small signal source comes with its own RS and VS. This is okay? Does connecting the small signal source change anything in your operating point? Nothing, right? It is connected through a capacitor. How does the small signal circuit look like? What happens to IRF? So IRF being 0 means it has to be open circuit, right? And then I have this transistor connected like this. I will assume that the value of the capacitance is large enough such that it is a short at the frequency of Vs. Then you have M1 connected like this. And for now, let's say I have RL parallel RL. So far, okay? Now, I would like to simplify this circuit. So, if I connect, if the voltage here is some Vx, what is the current flowing into this node? What is in the small signal picture? The current through this transistor is going to be, so the gate to source voltage is Vx, which means a current Gm times Vx is flowing through this, which means the same Gm Vx has to come like this, right? Therefore, the same current is flowing like this. Okay? So, the current flowing this side is basically Gm times Vx. So, now I have a black box. If I apply Vx, a current Gm Vx is flowing into it, right? Then what can I replace this with? If I had a resistor of value 1 by Gm, then it has the same behavior. Is that clear? If I apply Vx to a resistor of value 1 by Gm, then the current flowing through that is going to be Gm times Vx. So then I can replace this entire thing with a resistor of value 1 by Gm. Okay. Now, quickly tell me what would be the value of Vx. You have Vs, Rs and another resistor of value 1 by Gm. This will be equal to Vs into one by Gm divided by Rs plus 1 by Gm. Okay. What do you expect this value to be? Will it be close to Vs or so this fraction? Will it be close to 1, larger than 1, smaller than 1? Definitely smaller than 1, right? Now, when you are designing this amplifier, we wanted the properties of both of these transistors to be same. We wanted IRF to get exactly reflected there. And you would design M1 for a large GM, right? Because you want a larger gain. Now, if you design for a large gain, and if M1 and M2 were identical, what comment can you make about 1 by GM? It's going to be small, right? So you did all of these nice things, but finally the moment you connect it, your Vx is going to be much, much smaller than Vs. Right? The gate to source potential appearing, the incremental gate to source potential appearing for M1 is much, much smaller than your signal source. Right? So this means something went wrong when we combined both the circuits. We have to make some correction in the circuit in the way how we are connecting the small signal source. So the one thing that we could do is I could connect some component here. Okay. I connect some component before connecting our intelligent battery to the M1 transistor, such that in this expression you will have, so you have the same component here and you have 1 by Gm plus something. Now, if I make this something to have very large impedance, right, then I can make sure that my Vx is almost equal to Vs. It doesn't matter that 1 by Gm is small. because this component is going to offer such a large impedance that the overall impedance is going to be much larger than RS. Right? Now what can I connect here? I could connect a very large resistance. Right? Now in the large signal picture, what do you want that component to act like? So if I connected some unknown component, now in the small signal picture, it has to offer a very large resistance. In the large signal picture, when we are calculating the operating points, we don't want any drop across that component. Right? So now if I connect a resistor and I make sure that this Rx is much larger than Rs, we are set for the small signal picture. Right? What happens in the large signal picture? What is the drop across this? IRF RS. So where is IRF flowing into? Right? So what is the current flowing through this path? Can a current flow like this? Right? It is to the gate of the transistor. So no current flows like this. Right? And no current can flow into this path also. Which means the current here is 0. So the entire IRF is flowing through M2. So no current flows through Rx. Therefore, the drop across this is going to be 0. So it doesn't affect our DC operating conditions, but it is offering a large impedance for the small signal picture. Is that clear? Okay. So you can do the analysis of this circuit and we'll continue in the next class. Thank you.